Have you guys worked with algebra tiles before?
Yeah, in middle school.
Back in middle school? That's fair enough. Some people are totally unfamiliar with them. So as we go through and explain how this picture is representing x plus 4 squared, let me bring up, I got this guy right here. I have my online algebra tiles. I found all kinds of cool things last year when we were virtual. It's like, since I couldn't give people things to manipulate, it's like, we have an online version. Move it around yourself. Okay, so the blue tiles that you have in front of you are the x squared tiles. The green ones are x, and the yellow ones are 1. Now, when we're talking about these as x squared and x and 1, we're talking about the area, the space inside. So all of this right here is x squared. How do you find the area for a square or a rectangle? Multiply. What do we multiply together? Length times width. So what would the length and the width be on this if I multiply those and I get x squared?
X4?
It would just be x. I'm going to have an x here and an x here, because when I multiply the length and the width together, I get x squared. That's the space inside. Does that make sense?
Mm-hmm.
Let's look at another easy one, and then we'll go look at the x tile, because I feel like that one gets confusing. What are the length and the width on this guy? 1. Because that's the only way I can multiply and get 1 as my answer, right? At least with whole numbers. What's the length and the width on this one?
X and 1.
Yeah. It is 1 unit wide. Notice it's the same width as this tile right here. And the length is x, because it's the same as this tile here. And if I do 1 times x, I get just x, which is this guy. So far, so good? So I want to take our attention back to what we were just looking at in your books, because I want to know how that arrangement of algebra tiles somehow is meant to represent this polynomial. So tell me on the picture what you notice about the way the tiles are arranged. What's up in the corner?
X squared.
An x squared tile is up in the corner. What's the length and the width on that guy again?
X times X.
X times x. So this is x, this is x, right? I'm going to look at the ones next. I've got how many of them?
6.
Yeah, it like makes its own little square here, right? 4 across here, and 4 when I look up and down. Okay, so 1 plus 1 plus 1 plus 1. What's 1 plus 1 plus 1 plus 1? 4. Sorry, I didn't realize that was still up on top of everything else. Same thing across the bottom, right? And then I've got these green ones. How many of them side by side?
4.
4 of them side by side. How wide did we say they were again?
4. Or X?
How wide? This way?
1.
1 unit. So it's 1 unit wide, plus another 1, plus another 1, plus another 1. And I'm adding that to the x that was there already, right? So how long is it all the way across that side?
X plus 4.
X plus 4. All right, let's look at the other side. How many do we have again?
4.
4 of them. When I'm looking at this side of this picture, I'm looking at how wide they are there, which we said was how big? 1. So I have 1 plus 1 plus 1 plus 1, which is what? 4. So the entire side is
4 plus
x plus 4, or 4 plus x. Yep. X plus 4. Look at the bottom. Because what do you know about squares?
They are the same.
It's the same all the way around. How long is that piece? X. X plus 1 plus 1 plus 1 plus 1. That side is also how big?
4.
X plus 4. And I don't have room to write it off to the other side, but it's the exact same thing, right? So how does this arrangement of tiles represent this idea right here?
If you multiply the length times width, you get x plus 4 squared.
Length times width gives me area. If I look at the length of this rectangle, it's x plus 4. If I look at the width of this rectangle, it is also x plus 4. And I'm multiplying those together. Where did the squared come from?
Because you're multiplying it by itself, you can just put squared.
Yes. These two are exactly the same, 100% identical. If I take something and I multiply it by itself, it is that thing squared. So I would have x plus 4 squared. So far, so good? All right. I want you guys to look like in the middle-ish of the page. You guys see all those algebra tiles that are drawn there for you? I want you to open up your little plastic bags of algebra tiles, and I want you to count out exactly what they show there. So you're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of the little yellow ones. That's this plus 10 right here. How many of the green rectangles do you need? 8. 1, 2, 3, 4, 5, 6, 7, 8. And how many of the large blue squares? Just one of them. You only have a single x squared there. I want you to try to take those tiles after you've counted them out and you have exactly what it shows in the picture. And I want you to take those and try to arrange them into a perfect square. What does a perfect square look like?
All the ones are exactly the same.
Yes. All the sides are the same. All right. Play around with this for a little bit. If you guys hit any problems or you get stuck, turn to page 89 and answer the questions there to help you work through that. Yes, 8 of the green ones, 10 of the yellow ones, and 1 of the big blue ones. Yep. has to form a perfect and complete square. No missing pieces, all four sides are the same. That is an annoying sound. Get stuck, I want you to turn to page 89, read and answer the questions there to help you. If you haven't managed to get a perfect square from what I gave you, turn to page 89. Read and answer those questions. Put that in your collection. So, the best way I can describe this, and I'm going to say pretty much the same thing for the whole class here in just a minute. If you want to buy something, and you don't have quite enough money for it, you're just looking at your prom dress, and you're like $50 short, but it's on sale. So you ask your mom, you're like, can I have $50? She's like, have? No. Borrow? Yes. What does it mean if you're borrowing it?
You'll have to pay them back eventually.
Yeah, so right now she's going to give it to you, but later she's going to take it away again. That is a net gain of 0. You weren't given anything, you didn't lose anything either. Does that make sense?
Yeah. So is that like another word for borrow in math?
Sort of. Like, she is going to give you something, right? In math, how do we give it?
By adding.
By adding.
Take it away.
But then you got to take it back away again. There you go. What problems are you guys running into, or did you run into as you were trying to arrange these? Not enough of the little yellow ones. Okay, so if I was going to allow you to have some extra tiles, how many would you need? 6 extra tiles. If we ignored the yellow pieces for just a minute, how many total little ones would you need? Like, ignore what you already have. If you're just working with the blue one and the green ones, and you start building your square, how many yellow ones would you need to finish it out total? 16 total. We're not allowed to change our original expression at all. And so the next question is hitting on that. How could we keep the net gain at 0? Here's the best way I've been able to think of to explain what a net gain is. You head out to the store. The thing that you've been wanting for a long time is on sale, but you're like $50 short. So you go and ask your mom, please, 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 can I have $50? I want to go buy this thing. It's on sale right now. She's like, have? No. Borrow? Yes. I'll let you borrow $50. What's the difference between her giving you $50 and borrowing? You have to pay it back. So at the end of the day, if you borrow it from her, you didn't actually get that extra stuff because you're going to have to pay it back. That is a net gain of 0. In math, how would we represent her giving you that money? Addition. But then you got to pay it back. Subtraction. And it's going to be the same amount, right? So whatever she gives you, whatever you add, you're going to have to take back away again. The vertex form for this, sorry, let me look at it. I was going to look at the other side. X plus 4 squared minus 6. Why does it have a minus 6? Yes. You're going to have to pay back what you borrowed. So x squared plus 8x plus 16 you said was going to let us make this into a perfect square, but then I got to pay back that 16. I had 10 to begin with, so we're still like in debt 6, right? So where did the x plus 4 part come from?
Because if you distribute, you get the exact number.
Yes. That x plus 4 squared, that's the square, that's the sides on the square that I would make out of this. This would be x plus 4 squared, and here's my minus 6. I want you guys to flip over to page 90 now. Flip over to page 90. We already talked about how this side is x. This is how wide? 4. Put that together. Over here, it's the exact same story, x, and this right here is 4. And we're going to put those together. So that is x plus 4 squared. This is why I don't call it a box when we do factoring or anything. It's why I call it an area model. Everything that we've just been doing with the tiles is based on length times width. It works because of the area of triangles. So I'm going to try to reverse this process. I'm going to try to think through what we just did. We're going to fill these in down at the bottom of page 90. I need to make perfect squares. What did you tell me about perfect squares again? They're the same all the way around. On an x squared tile, is that already a square? Yeah. So I can let one of these represent x squared. We had to arrange the green ones on the sides, right? But I want my length and my width to be exactly the same. How many of these am I working with here? Close. Negative 8x. So how am I going to ensure that the two sides are the same? I want the two sides to be exactly the same. Yes, one of them will be 4, the other one will be 4. In this case, negatives, right? I'm going to take whatever they gave me. I'm going to cut it in half. And I'm going to put half in each of these.
One would be negative 4, right?
Yep.
Oh, -2.
Negative 4x and
2.
not 2,
Positive 4.
not positive 4. It's another
Negative 4.
-4. Those two have to be identical, or else my two sides won't come out to be identical. So whatever I put in one little box, I got to put the exact same thing in the other. It has to be half of whatever the green rectangle amount is. So I'm going to think about these sides. How big would this side up here be? Yep. X minus 4. What about the other side? X minus 4 over here as well. Tell me how you got that, Nasiba.
Oh, I multiplied -4 by -4.
Negative 4 by negative 4. Absolutely correct. This is what we're going to need if we were going to make a perfect square out of it, right? So here's what I want you to write down now. We already had the x squared. We already had the negative 8x. You told me you need how much? We need 16 to finish this out. But I need to keep my net gain at 0. So if I add 16 to it, I'm borrowing that, right? What do I have to do to keep it balanced? Subtract that 16. This is the big idea that I want to see on your paper. Let's look at the next one. Help me fill this in. X squared goes here. Is it -5 or is it different? Yeah. Cut this in half. So it's going to be a -5x and a -5x. Yes, down here is going to be a positive 25 because we have to do -5 times -5. We already had the x squared. We already had the -10x. To make it a perfect square, I need what? I need 25, so I'm going to plus 25 so that I can finish it. And then subtract 25. How big would the sides of this be? Yes, x minus 5 and x minus 5. Turn the page. We're going to do the one at the top together, and then you guys are going to do the other two on your own. Why did I want to do the first one with you on the next page? Does it not divide in half, or does it just not divide in half nicely? Yes. If I take this guy right here and I cut it in half, because I'm always cutting it in half, so those two boxes here and here can be the same, because I need it to be a square. They've got to be the same or else it's not a square. You said it's going to be how much when I cut it in half? -1.5 when I cut it in half. So -1.5x, -1.5x. Where do I put my x squared at? Yep. So x squared goes here. What do I need down here? -2.25. How did you get that? I don't know. I thought I was repeating what you said. Tell me how you got that. Yes. -1.5 times -1.5. That's how we're getting this number right here. So I had an x squared. I had a -3x. To finish this, I need what? Yes, plus 2.25, and then we're going to subtract it right back out again. How big are the sides? Absolutely correct. Please do D and E on your own. Mm-hmm.
So since we're adding this, when I subtract this first, and then add it back,
So because this is what you need and this is a
Mhm.
positive, you
Yeah.
have to add that here,
Mm-hmm.
but then you got to keep your net gain at 0, so then you minus it back out again.
Okay.
Mhm. Just like when you go to borrow money, you get it first,
Mhm.
then you pay it back.
These are the
Hmm.
So like, if I put -7x, that would be -15.
Wait, what?
Oh wait,
Is that going to be a minus or a plus? Plus. Yep. Hmm?
would that be x plus 7?
Yes. Mm-hmm. That one is absolutely correct. Yes. That is right.
So would I add or multiply?
For what? Why do you have one that's a plus and one that's a minus? If I add these two together, like, are these two sides exactly the same? They're exactly the same. Mm-hmm. Tell me about squares.
Squares are automatic.
Is that? No. What are you cutting in half? No. It's coming from here. What are you cutting in half? Is that positive or negative? If you take something that's positive and cut it in half, it's still positive.
So if I add these, it would be like +14.
Yep, and that's what that is, right there. Mm-mm. What's 7 times 7?
49.
Not negative 49. That's what you need. You don't have it, so that's what you need to borrow. Then you'll have to pay it back. So you're going to add it, but you're going to minus it right back out. Those are correct. Mm-hmm.
Yeah.
That. You forgot your, that's not an X right there. I should probably put a dot there instead. I was just afraid it's going to get confused with a decimal point. Like, I feel like I don't have a good way of writing that we're timesing those two together.
Yeah. So, since you can't cut that in half,
You can't cut that in half? If you have $14, could you give half of it to Kyla and half of it to me?
so put 7.
Mm-hmm. Love it. This number right here is what you need to add as a friend. Help me fill this in. Part D. What goes in the blue box? X squared. In the green? 7x and 7x. These have to be identical. Same sign, same numbers, same variables, identical, or else the two sides don't come out to be the same. Remember, again, to get that, we cut this in half. And so that's where that 7x came from. So what do I need to finish this out? I need 49. 7 times 7. So how big are each of my sides? Yep. X plus 7. And the other side is also x plus 7. Because remember, we're building squares here. All right, so I already had the x squared. I already had the 14x. Add 49, that's what I need to borrow to finish this square that I just built. But they weren't just nice and generous and gave it to me. I had to borrow it. So I have to pay it back again. How's the last one work out?
You gotta divide 5 by 2, you get 2.5.
Yep, we got to divide the 5 by 2. Right here, cut it in half. You got 2.5x, so I have x squared here, 2.5x, 2.5x. You said 6.25? And how did you get that again? 2.5 times another 2.5. That's how we're getting that number. How big are my sides? Love it. X plus 2.5, x plus 2.5. I had the x squared. I had the 5x. Add 6.25, because that's what I need to finish this out. And then you subtract it again, because nobody is being that generous with us. We got to pay it back every time. We're going to look at one last thing on page 92. I have x plus 6 minus 10. I want to write this into vertex form. So first I need a perfect square. To find my perfect square, I want you guys to ignore the minus 10 part. So if I ignore the minus 10, and I've got my attention just focused on the x squared and the plus 6x. Talk to me about what I need to do to fill in this box. Yep. X squared, 3x, 3x, because we always take this guy and cut it in half. So I need what? 9. 3 times 3 gives me 9. Yep. Okay, so I have x squared plus 6x. You said I'm going to add what? And then subtract 9. Remember how I was ignoring that minus 10? I need to have it down here, though. Do you guys agree that this right here has the exact same value as what I started with? Yeah. Minus 9 plus 9, those would cancel each other out, and I get right back to where I was, right? Brennan, the minus 10 came from right here. I ignored it to make my box over there. Yep. I ignored it for the box. Now to write this down, I want something that's exact same meaning as what I started with. So far, so good? Which tiles got used to make that square? Blue, green, and yellow. So these pieces, right? That makes my square. Paying back that 9 is not part of my square, is it? Nope. How big are the sides of that square? X plus 3 and x plus 3.
Should that be a 10 instead of 19?
Yes, it should be a 10 instead of a 19. Thank you. I got too used to writing my 9s and got distracted, and my mouth goes, my hand writes. Okay, so you said x plus 3 and x plus 3. So I can take this square right here. These are the pieces of my square. And I can write that as x plus 3 times x plus 3, right? Because length times width is the same thing as the area. Is there a better way to write that? Instead of timesing it by itself?
X plus 3 squared.
X plus 3 squared. Let's combine our like terms at the back.
9 is 19.
Yep. Oh, I didn't want that as a circle. minus 19. That is vertex form. What's the vertex here?
Well, -3 and -19.
Negative 3, negative 19 would be my vertex. Where was the y-intercept of this?
-19.
Where's the y-intercept?
Isn't it -19?
No,
Isn't it negative 10?
it's negative 10. Why is it negative 10?
You gotta look back at your original equation.
Standard form tells me y-intercept. Vertex form tells me the vertex. We're going to keep practicing with this tomorrow. This is the last big skill that we need because we can go from factored or vertex form into standard form. We practiced that yesterday. We can go from standard form into factored form by doing the X and the area model. And now we've talked about how to go into vertex form. So tomorrow we're just going to practice a little bit more with vertex form. Next week, Monday, Tuesday, Wednesday, we're going to review for your test. Test is a week from today. You guys should already have a review for that. If you don't have a review for the test, they're over there in that tray where it says reviews on my cart. Please grab one. There's maybe one question on that review that you can't do yet, just based on the practice that we're going to do tomorrow. Because we'll look at some special cases and some oddball things that can happen.
Do you know how many tests you have left or what happened to your review?
In this class, there's the second half of this after break where we do the solving with quadratics. And then we have one more unit after that. So after the test next Thursday, there's 2 more tests before we get ready for the final exam. Last thing I wanted to point out is next week when we did our review, when we do our review, some of those days are going to be independent work time on the review. Some of those days I'm going to have some activities that get your mind working to practice the skills that you're going to need in order to be successful on the test. All right?